For projectile motion, when angle of projection is not given, you treat the question like normal motion under gravity, which we learned in our previous class. So the equation of motion we use for solving problems in motion under gravity, those equations hold true for projectile motion also. And in doing that, we call it the first principle. The first principle, that is solving problem using the first principle. On the other hand, when the angle of projection is involved, then we use special formula which we are going to derive in this class. So we have one question here, example 1. It says a tennis ball is projected horizontally from the top of a vertical cliff 50-meter high with a velocity of 10 meters per second. Find the time taken to reach the ground, the vertical component of the velocity when the ball hits the ground, the distance from the foot of the cliff where the ball hits the ground. So let me try and represent this in a diagram for a better understanding. So this is the cliff. A cliff is a platform, just like let me say a hill. Now, on this cliff, you have a tennis ball, and then somebody with tennis ball horizontally. Because of this initial velocity along the horizontal axis, you expect the tennis ball, when it is coming down, it's going to trace this type of path and then land on the floor. Now, it tracing this curved path because of that initial velocity of projection. Assuming there's no initial velocity of projection, let's assume this guy just released the ball from a height. Then the ball will likely land at the foot of the cliff instead of traveling away from the foot of the cliff. So with that information, we can solve the question. Now it says calculate the time taken to reach the ground. The time taken to reach the ground independent of the initial velocity of projection. It is independent because this thing starts falling to the ground the moment it is off the cliff. So let's assume the ball is somewhere here, then you kick it, of course, it's going to roll along the cliff first, then start coming to the ground once it's off the cliff. Now, the point I'm trying to make there now, why is it independent? Why is the time taking independent of the initial velocity of projection? When something is dropped from a height, whether there is initial velocity of projection or not, it is expected that that thing will come to the ground. So the time taken when this thing is falling from this point to the ground is independent of the velocity of projection here, because when you projected it is rolling along the cliff, it starts coming to the floor when it is off the cliff. So what the initial velocity of projection achieve in this case is to make the ball to roll off the cliff and then travel down to this point. So the time taken is totally independent of that initial velocity of projection. The t we don't know, but we know the height of the cliff. The ball is the same height with the cliff, and that is the distance. And the distance traveled by the ball is 50 meters. The ball is falling to the ground, so it's under the influence of gravity. As such, it has an acceleration of 9.8 meters per second square. And then we say when something is released from a height, initial velocity is zero, because this thing starts coming to the ground when it is off the cliff. So we assume that it is released from a height, not as a result of the initial velocity of projection. So now we have T, S, G, and U. Which of the equations contain T, S, G, and U? So let's write out the equation. So we can select the proper one. The first one is V is equal to U plus or minus GT. The second one, S equal to UT plus or minus half GT squared. And the third one, V squared equal to U squared plus or minus 2GS. So we have S, we are looking for T, we have G, we have U. So which of the equation contain those three things there, or four? Definitely is this one here. The second one, which is S is UT plus or minus half GT squared. ut, but the ball is falling to the ground. That means acceleration due to gravity is positive. So we use plus here, gt squared. S is 50, u is 0. So everything here, the first term here will be 0. 0 times t is 0. So I will just ignore this first term and move to this. G is 9.8 and times t squared. 50 is equal to 9.8 divided by 2, 4.9 to 4.9 t squared. Dividing both sides by 4.9, t squared is equal to 50 divided by 4.9, which is 50 divided by 4.9, that is 10.20. T therefore is square root of 10.20, which is 3.2 approximately. So the time taken to reach the ground is 3.2. Then question B says the vertical component of the velocity when the ball hits the ground. Okay. Again, the vertical component of the velocity when the ball hits the ground is independent of the initial velocity of projection, because whether it is projected horizontally from this point on, we are assuming that this ball falls from a height. And when something falls from a height, initial velocity is zero. And the time taken for the ball to fall to the ground, we just calculated it to be 3.1, we have 3.2, 3.2 seconds. Then it's under the influence of gravity. So G is 9.8 meter per second square. And the distance is the height of the cliff, which is 50 meters. We have to find the final velocity, v, which we don't know. Now, which of the equations contain u, t, g, s, and v? Now, we have almost all the parameters here. So, any of the equations that contain v will help us to get the value of the vertical component of the velocity. So, I'm going to use the last one, which is v squared equal to u squared plus 2gs. So, v squared equal to u is 0, 0 plus 2 times 9.8 times the distance, which is 5, 50. V squared, therefore, is 2 times 9.8 times 50. That is 980. V, therefore, is square root of 980. And square root of 980, 31.3 meter per second. That is the vertical component of the velocity as it hits the ground. Last question, which is question C, is the distance from the foot of the cliff where the ball hits the ground. Now, look at where the ball hits the ground, away from the foot of the cliff. The foot of the cliff is here. The ball moved all the way like this and then hit the ground here because of the initial velocity of projection. If this guy just dropped the ball from a height without kicking it with an initial velocity of projection along the horizontal axis, you agree with me the ball will just fall straight to the ground and land around the foot of the cliff. But in this case, the ball landed here is as a result of this velocity of projection along the horizontal axis. So the point I'm trying to make here is this distance away from the foot of the cliff is dependent on the velocity of projection. So in that case, the initial velocity is the velocity of projection, which is 10 meters per second, according to the question. So u is equal to 10 meters per second. And we said that when something moves down in a parabolic path like this, the horizontal component of the velocity is independent of gravity, right? So G is 0 in this case. G is 0 because the horizontal component of velocity is independent of acceleration. Then the time taken for the ball to hit the ground, we already calculated it, which is 3.2 seconds. So t is 3.2 seconds. So we s equal to, we don't know. So which of the equation has u, g, p, and s? That should be s equal to ut plus half gt squared. And g is 0. Therefore, everything here, this half gt squared will be 0. To be 0 multiplied by anything is 0. So we concentrate on only this ut. So s equal to initial velocity of projection is 10. and the time taken for the ball to hit the ground is 3.2. 10 times 3.2 is 32. But the distance away from the foot of the cliff is 32 meters. That is for a simple case of projectile.